Hello, thank you all for coming to my very first conference presentation. This is joint work with my supervisor, Rida Laraki. And well, this is a new way of considering belief aggregation, for which we found mechanisms that were strategy-proof. The presentation will be first we're going to explain to how we reached this model we're working on. Then I'll go into detail about the model, and finally I'll be showing you the contributions in the anonymous case for simplicity's sake and time's sake. Okay, so belief aggregation is basically the idea of asking experts for their opinion, which we are probably going to provide in terms of probabilities, and then aggregating it into one probability function distribution, which you'll be using for whatever you need afterwards. So the example here is, let's ask our experts what temperature is going to be in 10 years' time. So, well, they don't actually have the ability to see the future, so they'll give you what they believe it's going to be according to the models, and then you're going to have to work from those distributions. Okay, so the first problem we have is that experts don't actually know, so these are just opinions. And in a certain number of situations we're considering, they might actually have their own incentive and don't want to be honest in what they're saying. They just want the outcome to be as close to what they want. Okay, so we're dealing with situations without money transfers. Basically, the idea being that the situation is in 10 years' time, and the consequences could be so catastrophic that money is just not relevant to the situation. Okay, so very quickly on literature about aggregation, belief aggregation in situation without money transfers. There's very little of it. And most of it reaches impossibility results. In order to have mechanisms, you need very strict constraints on the domains of what can be provided. And the only positive results we could find was the Freeman paper on moving methods in EC'22. Which are somewhat very different from what we're doing, because they're considered neutral alternatives, and well, we're not. So why aren't we not considering neutral alternatives? Well, because if again our example with global warming, well, the alternatives are ordered. It's the temperatures, and therefore it doesn't make sense to consider each alternative to be separate and to be treated equally, given the fact that they are dependent on each other. One other question we have to do, because, well, we're going to have to restrict our domain, is how are we going to consider utility functions? And what is natural, given the literature, is to use the LP norms. And so the first thing we're going to do is try that, but this doesn't really work very well. So why doesn't that work very well? Well, let's consider an expert who is very single-minded and believes that alternative one, the smallest alternative, is the only possible outcome. So his whole probability function is a direct in alternative one. And the only other outcomes that we can get from the mechanism would be a single-mindedness in alternative 2 or single-mindedness in the very last alternative. So from the perspective of this expert, well, alternative 2 should be better than the final alternative, because even though it's not what he believes, it's closer in terms of our ordered alternatives. But if we use the LP distance in the normal distributions, we're going to find that no matter what LP norm we consider, we do not distinguish the second position from the last position, if we were this expert. However, if we decide to consider the cumulative space instead of the distribution space, then by using the LP norms, we do have this distinguishment, and we do have that this expert prefers the second alternative to the last alternative. So it makes more sense in terms of what we're representing. So basically, that's what we do in our paper. We're simply considering that our utilities are going to be defined using the cumulative space instead of a distribution space. So in order to obtain our results, the actual only paper you need to know is the strategy proofness and in the single peakedness paper from Moulin in 1980. And every one of our results is a consequence of this paper. So I'm basically just going to go very quickly over his results. So basically here you're considering a road, and you have to decide where the library is going to be on that road. And everybody living along the road can give his opinion. So people would usually prefer the library to be built either close to their home or close to the school. And you can consider that the utility function is going to be increasing up to a peak, the ideal position, and then decreasing afterwards. And with these assumptions, we do have that strategy proofness being the idea that everybody doesn't benefit from lying. There is a unique way of making the methods, which is to choose n+1 constant values, known as phantom values, and considering the peaks of players, and you take the median of his whole set, and this is going to be your outcome. This characterizes all these one strategy proofs methods for this choosing the library position along the road. Okay, so now that we've gone very quickly through this known results, let's just go through our model. So we have our experts. We have our linearly ordered set of alternatives. This can be a broad subset of R. Usually we recommend you consider intervals, R itself, or finite order, because those are what you're going to find most commonly in real life situations. But the result does expand to the whole broad cells. So yes, we have our sets of probability distributions, the cumulatives, the function that goes from one to the other. This is interesting to have the three, because axioms tend to be defined according to the probability distribution, not the cumulative space. So we have to go from one to the other in order to be specific. And then again, you have the probability profile, which is what everybody's, all experts' opinions, and removing one. Okay, now that we've done all of that, we can go to our actual definition of strategy proofness in this state. So the intuition is actually very simple. We're simply going to consider that we are strategy proof according to each threshold. In the case of global warming, you don't actually care about what the exact probability of increasing from 3 degrees is. What matters is what the probability of having crossed that threshold. And so the idea is, well, since what's important is crossing thresholds, we're going to define everything according to thresholds, which again makes a lot of sense since we're talking about the cumulative space. And this is very interesting, because with this definition of level strategy proofness, we are strategy proof no matter what LP norm we're considering. And we believe that this is actually characterization. So if we are strategy proof according to every one of the LP norms in the cumulative space, we believe that this comes back to this level strategy proofness definition. Okay. So now that we've got all that, let's go forward with the contributions. So, unsurprisingly, we now have a theorem that provides all mechanisms that is, as I said, an extension of a previous result. So again, you have a median of what is now, you consider for one threshold, what everybody's opinion is about that threshold, and a series of functions in the position for that threshold. These functions basically just replace the phantom values we had previously. So it's easier to see an example. So on the left, you have 3 experts with colors, blue, red, and purple, and 2 black functions, which are what replaced the phantom values previously. And what we need to do in order to get our result is simply take the median for each threshold, in other words, for each vertical line of value of the 5 values we have. And that's what we find on the right. In green is your outcome. So all you need to do is basically find all possible black lines. So going back to my theorem, what we need for the lines to work is basically we just need n+1 of them. They have to be increasing, and one of them has to tend to 1. Basically, the only things we need is for the outcome to end up being a cumulative distribution. And all the consequences what we're writing here are just there to make sure that we end up with a cumulative distribution. And in order to have a unanimity, which is this idea of if every expert gives the same expertise, the outcome has to be that expertise. We just need our first black line to be on the bottom and our last one to be on the top, which I've already done here. So here you only have 2 black lines instead of 4 because we've got one of them that's a constant in 0, one of them that's a constant in 1, and therefore they don't need to appear in the graphs. Okay. So now that we've done this, what can we add as interesting properties? Well, one interesting property is if all the experts agree on something being completely impossible. But we would like the aggregation method to also agree about that. So if everybody agrees that this interval is never going to happen, this interval should not happen in the outcome. And in order to obtain that, we can simply do it by saying that our black lines, our phantom functions, are constants. And one of them has to be equal to 0, one of them has to be equal to 1. That's all it takes. So it's very easy to obtain this certainty preservation property using our method. Another interesting property would be plausibility preservation. Now this is the idea that you have an interval and everybody agrees that this interval is plausible. So in other words, that probability of it happening is surely not equal to 0. Okay, and in order to obtain that, we also have a very simple characterization, which is going to be that it's either we're equal to 0 or we're equal to 1, or we're strictly increasing between the two. So that's the only thing that we need on the black lines in order to attain these two properties. So example, on the left side you have certainty preservation. I simply put my functions, my phantom functions as constants, and now I have that if all experts agree something is impossible, the outcome is going to have it, this is impossible. And on the right side, I have strictly increasing things, and therefore I obtain this idea that I'm plausibly preserving. If everybody agrees something is plausible, the outcome will say it's plausible. Okay, and now a simple question, what happens if we want both of them? And in order to describe these, the idea is simply to say that we're going to consider each time an order function as to define our method, and that's going to say, for example, so the order functions is the k smallest value if you take constants. And so we're going to consider for example, min1, in our cumulative space, each threshold, we're considering the minimum choice the expert provided. And that with these definitions of using the order functions to define our properties, we have all the methods that are both certainty preserving and plausibility preserving. Interestingly, it would be the middlemost cumulative, so you're using the median of experts here. And what's interesting about the middlemost cumulative is that it is the one that provides welfare maximization for the L1 norm. So it's a rather interesting method. On our example, you just took the middle expert's choice and have obtained this. Another interesting method is the proportional cumulative. So the idea here is you're going to have two experts that are single-minded about alternative 1, one expert that's single-minded about alternative 3. We would like the outcome to be 2/3 in alternative 1, 1/3 in alternative 3. And this ends up with a characterization of a single existing method where our phantoms are uniformly distributed along the 0, 1 line and are all constants. Okay, and what is very interesting about this proportional cumulative is that if experts are dominated, so dominate is this idea that in the cumulative space they are each one after the other and they don't cross. And what happens is that if this happens, so this is what we see here, then each expert in the outcome is going to wait for exactly the same amount. So in a way, we've managed to ensure that each expert has the same actual value in the outcome. So in the anonymous case, this is rather interesting. In the middlemost cumulative, can also be described, again, using dominated opinions, as the one that's going to return the expertise of one expert. So these two methods are very interesting when you're considering dominated opinions. Okay, and so moving on to the extensions we have. Our characterizations can very easily move on to the non-anonymous case. You just replace the Moulin's anonymous description to the non-anonymous we found in his paper. It's in the annex. And if you want to replace a proportional cumulative by something that's non-anonymous, you can simply replace them by weighted cumulatives where each voter has a specific weights. And again, in the dominated case, you're going to end up with them each having the exact value of a weight. If you want, you can also use our other paper to see other characterizations that will provide you the same non-anonymous characterizations, which are very interesting. We also prove a few impossible results in this paper, but they are not as interesting since, as I said, the idea is for once we have a positive result for belief aggregation. And we also suggest a way of using this to do actual voting in situations where you're not quite sure about what you're voting. So let's say you have a candidate and you're like, this 80% chance he's going to be great and a 20% chance he's going to be awful. And you can now vote with that idea of saying, okay, 20% chance he's awful, 80% chance he's great, and we can build a voting mechanism to choose a candidate with this method. Thank you all for your attention.
Any questions? Since we're also 6 p.m., so yeah, let's end here. Let's thank all the speakers one more time.